thing. So this institute I work for, always I couldn't say that very difficult things. So finite elements were not the thing to do. So I'm talking about very simple things, and on the other thing, nowadays I just have my private logo, the Franz and this Franz, and so I want to take this opportunity to thank those people who give me opportunity to work, that is joinable from NK. And so I'm going to also to speak about a more simple thing, just variable resolution, not adaptive, but variable. And it has some applications in weather prediction, and also it has some difficulties. People doing it, just having a variable resolution and just keeping it a variable while a thing of different scales comes to it, makes some difficulties, and I will say some the motivation why variables are such a good thing, and some results and some methods. These are simple methods, and so actually my point is that I need uniform, relatively high resolution to be successful. So anybody here can contradict me. As soon as you have a method which drops in order at special points and still is okay, you are right. But I go through a number of methods which were okay and have no problems, and they all have the property such as finite elements and spectral elements that whatever point you are, ever at a pole or at a point of change in resolution, it doesn't change accuracy or order of approximation. So this is my hypothesis, and I hope everybody can say, oh, my model just is has not this property and still has no problem, and they have some results. So I use rather simple method, this L-Galerkin method. It's not classical Galerkin, it's just simpler than it. So, but I'm not going very much on what it is. I will say that at another time. So these are the grids I'm interested in. First, these triangular grids on the sphere. You have these special points. You see the triangles have not the same size as the other one, and there is a tendency with some methods at these pentagon points to kind of make lots of noise. The other thing I'm very keen on is having atmospheric layers which go into the mountains. They create these extremely small discretization elements, but they have the advantage of giving more accuracy to the representation of orography, because numerical errors, if you do it, terrain followings have a tendency to make problems, and I will give some results here. The other thing is grid refinement, and I want to point out that here the grid I draw is another one. I have here the dual grid, so each grid point is surrounded by the grid cell. If I take this grid with here, the interaction grid, I connect these points, you see there is in this area triangles appearance where here the interaction grid is the same quadrilateral as the other one. So yes, the dual grids, this is for the hexagon. It looks nice, and I just want to say this triangles, this is the interaction grid. I don't have any use for the dual grids, these hexagons. I don't think if you are interested in a high approximation order uniformly, it's very hard to achieve with the dual grid. So I just forget it. So it is used with a finite volume method and constant basis functions. There are more complete fancy versions of this, but I'm not in this fancy method. So, and they have a tendency of dropping order to 1 if the grid becomes irregular. So I'm interested in the higher order, and I do it on serendipity grids, which is actually the higher order finite element grids. I use them. and say it's much easier to have the high order with them. And with this finite element space, it's the same, but I use the L-Galerkin method, which makes it simpler. Then each node point has mass mass in more than one cells. That's the difference to this dual grid. And it makes life so much easier. And they have a different order of representation. So the degree of, so in each cell of the interaction grid, I represent the field by polynomials, and the order of the polynomials is the representation order. So the grid can have an order, and so grids are normally in grids use are very low. Finite elements are appearing in one very often. It's most popular in one, but you can have higher ones. You have spectral elements. They somehow start at order 4 for some reason. And fourth order finite difference are done on the one thing, and the serendipity you can have anything, but I don't think it's reasonable to go beyond 3. So, so why do we do it? So irregular resolution is clear why you want to have it, but the polygonal grids of the sphere are popular because they go very much with a high, with multiprocessing. And the cut cells offer advantages. I want to show you there is even some evidence that the spill of forecast gets better than. So let's go for the cut cells. So I must make the point, real application I have done only for 3-dimensional mesoscale models, because before my pension that was my work. The other things tend to be rather simple. So this is actually a vertical velocity forecasted with these cut cells. This is actually the operational model of that time we had used. Vertical velocity is something you couldn't show to forecasters. It just is too kind of not very looking very nice. Here you see this is actually where we are. This is France, England is here, and there is a front going through, and the front is showing up by a kind of vertical velocity band, as it should be here also, but it's totally disguised under noise.
What level is that at, Jürgen?
Sorry?
What level are you exactly?
And I think it's about 850 millibar. And so here is then a cross section through here, and then it's a time goes here. So in the operational version, it somehow, yes, not very much structure in it. So here it goes in time smoothly down. So that is actually an application of variable resolution only near mountains. And it is, I did not go to the high order there. It remains the representation order rather low there. And so we did altogether 100 cases. These are the first 50 of them. It looks like this, that the RMSE error is, oh no, somehow the RMSE error is somehow reduced. I think it's quite a nice reducing for 24 hours. Because I didn't have any opportunity to make longer forecasts, so then that would be interesting, of course. So now the numerical approaches which are on the market. The finite volumes, and I don't go into it because I think it's difficult to go beyond on irregular grids first order. Finite elements are okay, but I don't think I can sell them anybody in its original form, classical Galerkin, because they have a mass matrix which has to be solved, and it goes very difficult with multiprocessing. I think the way it is used is by approximating the mass matrix, and then they become, have another name, they are called spectral elements. And there are some reason used only for order 4 or higher. So I suggest the L-Galerkin method. I don't go very much in what it is, just it is totally local by nature, I don't approximate it to become local, but it is local from the beginning, and it preserves, if the equation is conserving, it conserves also, and it works on serendipity grids. Yes, it has function system, I go over this. It works, I mean, it's a function system method, a basis function method, like a Galerkin. This is serendipity grid. Order 1, yes, everybody knows it's finite difference method. In squares, it's more popular. And then if you add points on the side, you get the order 2 serendipity and the order 3. So it comes from omitting points from the full grid, omitting points here in the middle. That is because if you do that, you have a more uniform order of the polynomials for interpolation. If you have a point here in the middle, or here, you have these 4 points in the middle, then in x and y, if in x the order goes to 3, in y it does, you have a 9th order polynomial, and they don't do any good. It essentially means that you carry around lots of zeros in your method. So you can leave these points out without doing much damage.
Is that not the case that, I mean, serendipity grids are really just a quad thing, right? I mean, that's just finite.
Sorry?
The degrees of freedom you're showing on the left are just standard Lagrange element degrees of freedom.
Yes, it is. This is equivalent to the full grid. Yes.
Yeah, it's only on a.
It is on the square that you save these points, but still it has the property that the interpolation function here is actually exact. That you have third order polynomials only in each triangle.
Sure, but you just get that because you're on a simplex.
Yes. So, but actually, my applications so far are mainly on squares, even though I think if the grid really becomes irregular, triangles have their advantages, and in the applications I use, they need not all be degrees of freedom. You can create some by interpolation, and then you get all kind of a zoo of methods. So that is what serendipity is, that's clear. And so, yes, this is the point. You can have these extra points. These are the main node points. They define the first order part of the field. And these points you can get by interpolation or as dynamic fields. If you have them by interpolation, you get other numerical methods. You can actually show, if you use linear interpolation and do that, you can the whole Arakawa family of schemes you can derive from this kind of grid. I tend to use the high order approach. Yes, this actually shows that in the triangular element you get the full grid. I mean, you had the full grid. It is equivalent to a rhomboid with a full grid. Then you can have triangulation. So this is actually what the cut cells could look like. It's a square grid, but you have divided into triangles. These yellow points you can have by interpolation. Then you still have grid points only at the edges. Also this point can be done by, and these are phantom points. If you define them, they define the field in the middle. But of course, the equations of motion you derive here reflect only the changes of the field here in the middle. You don't derive it formally. And yes, this is actually what I did. I saw this in a model. I say in one of our model it was. This is formal force or classical force order differences done on irregular meshes. And just doing it formally, that's not right. You have to look up how to do first order element discretization accounting for the third order. Then everything becomes much better and also conserving. So this is actually on the icosahedral mesh. It works very nice in third order. This is actually non-conserving, but these serendipity things you can use to make it conserving. And so now I do say a little bit on what it is. So you have an equation of motion, a divergence on the right-hand side. You discretize it by taking the function system and taking the divergence on the function system. And then you get to the original function system by doing a Galerkin operators. I call Galerkin every operator which goes from the space of continuous functions to the space of discontinuous functions. No, the other way around, which makes the discontinuous functions continuous. So classical Galerkin does it by least square, and it's extremely non-local. So I use a local version of it. And so this one is local and conserves, and it preserves the representation order. Representation order is the order of the polynomials. The order of your scheme can be very much higher, but I'm not so interested in it because this higher order, which is called superconvergence, can break down in situations, and that is so. Then here you have more things to do. The operator is a Galerkin operator, and I tend to use the local one. This is differentiation. It's the original. I mean, no discretization necessary for this because I have functions which I discretize, and of course I have the collocation operator. That is, if I have a function system, I take the function system at certain grid points and define the polynomials of relatively low order by that. And then I have the regularization operator, R, which kind of is applied to a continuous function and changes the function in such a way that the derivative is continuous, so it has that is differentiable. So what I call simple third order L Galerkin is that I regularize the right-hand side and then differentiate. No Galerkin operator here necessary because it's regularized in such a way that the divergence becomes continuous. And that is simple, and it's it has the easy thing with it that you can have any high order finite difference scheme. Whatever you take, you add these high order serendipity points, and then you get difference equation for these extra points, and the whole thing becomes conserving. So this is an example. Actually, order 2 grid standard. It's very nice. Actually, it's always the smallest wave, which is the smallest positive peak you can form in a grid. So only one point is different. So that looks much nicer than this, but both things are quite good. And I just want to compare these two. It's not this that it's much better. You see, it's a very, very big time step. It's one time step brings you more than one grid point. And here also, so I don't want to say that it is much worse, and this actually, I think this is quite interesting because it's also cheap. So these are more from this so. I don't want to go through them. You can have plenty of Galerkin by combining them like the averaging operators in an Arakawa scheme. So this is actually to show how it is, the stability. This is relative coarse resolution circular symmetric third order gravitational wave. It looks nice. You see in its course, you see here how the third order interpolation, you see the grid elements. They have actually 3 points on this shoulder. So you see, relative to resolution they are quite accurate. And here I want to make the point that it's simple, the examples, I can't help it. But I make the point that this is actually advection, homogeneous advection here. But that is quite clear. Third order methods are quite accurate, so that is like everybody would agree. But if I make the grid artificially irregular, it doesn't seem to notice. I know I have to do more complex examples, but anyway, that was what I able to do. So this is how I do stability. Very simple. I just make such a forecast with linear attraction, and if the forecast is all right, not blowing up, then my scheme is stable. And now I have here a whole range of things, and I have, in this simple method, found out the CFL number. So the normal order 1 grid, so that is center difference in another thing. On the O1 grid, the O1 method, it has 2.8. You can find it in books. Because I use fourth order Rangakuta, it has this kind of CFL on center differences. But you see there are something, order 2 grid with fourth order differences gives CFL of 4. It is a high order method which has a higher CFL than this, first order. And the same is here what I call simple, this O3 with fourth order difference, I call simple O3. It gives 3.8, it has higher CFL than the other. But the other thing is that I want to show is that you have plenty of choices to play around with these Elgalerkin operators. And this here is at the end. So I am at the representation order. All normal finite difference schemes have representation order 1. They need the so-called superconvergence to bring you at least to 2, because order 1 is a little bit not enough. And then you have finite elements. You get them from 1, 2, and 3. So if you are here, you don't need superconvergence. You have very often, even in irregular grids with finite elements, high order even for this representation. And high order finite differences clear, but spectral elements are in this area. The rapidity Elgalerkin you can have in any representation order you want. As I'm not interested in superconvergence, my own applications are here to order 3, and the methods are then also 3, and I know there are 3 whatever I do with them. Then I have for cut cells, of course I can do it also here, but all cut cell work existing, done, was also in this order 1. The simple reason was I was doing it for an operational system. So I come to my end, and this system was normal finite differences. I wanted to make as little changes as possible. So thank you very much.
So I'm going to dive in first. And typically, one of the really critical things that we spend ages worrying about is what an appropriate function space pair is for pressure and velocity. How does that work out in your spaces? Is it the analogs of the same spaces that we need, or does serendipity
I didn't worry much about it. I used always the same.
So do you not have pressure modes?
I don't have I didn't worry about this problem. Perhaps I should have, but I didn't. I did always the same. So for example, third order, I use third order for pressure and for velocities. So actually the high order I also did no staggering. The staggering I did only for first order representation. And I think it makes sense. So maybe I'm wrong in this respect, but it is, this is how I did it.
Jürgen, can you tell me how you circumvented your mass matrix? I didn't see a mass matrix.
Oh yes, I mean, I didn't well, I mean, I used my time, and I made a lecture in 2 weeks. I will do more on the equation. The simple thing is I do the differentiation in the continuous space that makes my space discontinuous. Then I have more than one amplitude for each grid point on the boundary. And so I have different modes, for example, the right hand, and in one dimension, the right hand and the left hand modes of linear basis functions. And I introduce point fluxes, which are now between the modes. So, and these fluxes are to be defined in such a way that if I apply them, the functions become continuous again. So it is not at all the least square Galerkin, which is a classical it is something different in such a way that it doesn't have kind of a mass metric in the first place. I don't have to approximate one, it doesn't appear.
I think I need to talk to you offline, okay.
Yes, good.
I think Bob has hand up.
Are these methods appropriate for representing geostropically balanced flows, especially in the limit where you don't know that your deformation radius is well resolved, as in the ocean?
One should probably think about it. I can't answer that question offhand. But, I mean, I did all these kind of tests which were in connection with our operational work, and I didn't go so deeply into it. Perhaps I should, but I don't know.
Hello, Professor. I was wondering, in your table 1, there is a conservation.
Yes.
Conservation of what? Momentum or the...
Now, you can, if you have more than one equation, you can have one conservation law, theoretically, for each equation you have. So, if you have the shallow water equation, one equation is for the density or the height field. So if this height field equation is in conservation law, it will automatically give you conservation for mass then. And in the normal way, if you formulate the equations also for momentum in conservation form, you will also get conservation of momentum. So you can actually have conservation of if your equation is not in conservation form. Then you have to put in more than analog, or Arakawa can do that also. You have to put in more than one Galerkin operator. I did it many years ago, and I think it's not worth the effort. So I am now thinking of the very simple things, and the simple thing is you have to put the equation into conservation form, so that on the right-hand side of your equation is a divergence. And this quantity, which is in conservation form, will be conserved. So if you have in a model about 10 variables, many moisture variables, and so on, you can conserve them all. But if you want to conserve energy, in addition to mass, you have to put in energy as a variable in your model, and then have the conservation form of it.
Great. Well, I think we should thank our speaker again.